Okay, our next speaker is Dave Minahan from Union Carbide, and he's going to speak to us, as you can see, on syngas to fuel alcohols and MTBE.
Okay, thank you, Nancy. I'd like to thank the organisers for inviting me to give the oral presentation today. Also, I'd like to thank Union Carbide for giving me the opportunity to come talk to you about this work. I'd also like to acknowledge my co-author, Dick Nagaki, who is a very fine surface scientist. For those of you who are involved with the Material Research Society, you'll know that Dick has been an organiser and will again be an organiser of one of the sessions at the MRS meetings, and he is responsible for a lot of the insights into the preparation of catalysts. This work has been carried out in conjunction with the Department of Energy through the Pittsburgh Energy and Technology Center. Seems I'm the first speaker, I guess, in the alcohol section. That gives me the opportunity to give people a little bit of an education for those who aren't familiar with the area, and to remind others of, first of all, the reasons why we're doing the work, and a little bit of the history behind alcohol synthesis catalysts from syngas. Of course, when we normally think of alcohol synthesis, we normally think of methanol as being the alcohol that we produce. And it's made very efficiently from syngas, using copper, zinc oxide, alumina with other promoters. But as an additive to the gasoline pool, methanol causes problems. First of all, if there's any water around, you get phase separation, and the Reid vapor pressure, which is the measured experimental apparent vapor pressure of the hydrocarbon, is increased. You can use mixtures of methanol and higher alcohols as a gasoline extender. The methanol and ethanol raise the octane rating, and higher alcohols act as a co-solvent, so you don't get the same degree of miscibility problems that you did in the straight methanol mix. In general, longer chain alcohols are better co-solvents than shorter chain ones, as you might imagine. However, unless an extremely effective and efficient mixed alcohols catalyst is discovered, methanol is still best made separately, with very high efficiencies and selectivities. I'm going to raise this up for those of you in the back, because I know it's difficult to see from back there. The most effective higher alcohol catalysts were those that are going to maximize the higher alcohol productivity and minimize the methanol formation, therefore. And you might imagine that an ideal product mix, and I put that forward just as a target to shoot for, will be one where you could make a 1-to-1 mole% mix of methanol and iso or tertiary butanol that you could then react downstream to make MTBE. Here are the major reactions that go on over the alcohol synthesis discussion this afternoon. The first, of course, is the alcohol formation from syngas. Notice that water is produced as a byproduct. The inefficiency in this reaction is the hydrocarbon formation. We do not want to do Fischer-Tropsch chemistry. We want to make the alcohols. But notice again that water is produced as a consequence of the Fischer-Tropsch chemistry. And the water-gas shift reaction is also a complication here. So the water that's produced either in reaction 1 or reaction 2 can react with carbon monoxide in the feed to produce carbon dioxide and hydrogen. And depending upon how efficient the catalysts are in the water-gas shift reaction will depend upon what the relative concentrations of water and CO2 are in the reactor. A brief review of the sorts of catalysts that have been tried for the synthesis of higher alcohols. And I've arbitrarily divided these into two major classes. The first is what I would regard as a low temperature. That's 250 to 300 degrees, modified methanol catalysts. There are a number of different classes of these. One that has been investigated by Lurgi and Snambragetti also by AFP, is based on copper metal plus an alkali. Here, copper cobalt catalysts. The copper is used essentially, if you like, as a methanol synthesis ingredient, and the cobalt allows you to grow the chain. So the combination of the two, at least conceptually, should give you the higher alcohols. What I want you to notice here is that the alcohol products that you get out obey the Anderson-Schultz-Flory distribution of linear alcohol products. So you see lots of methanol, smaller amounts of ethanol, and then normal propanol, normal butanol. And you can regard this as proceeding by classical CO insertion hydrogenation mechanism, even though that, of course, is not what actually happens on the surface. There are other materials that give an essentially Anderson-Schultz-Flory product distribution of linear products. Supported rhodium on silica. If this catalyst is optimized correctly, it can actually give you a lot more ethanol than you would expect from the regular Schultz-Flory distribution. And Union Carbide has patents on this, and also on the molysulfide material. All of these systems are modified with alkali. If you go back through history and find out where the first higher alcohol synthesis catalyst came from, it actually came from the work that came out of Germany 40 odd years ago now, where you take a modified spinel oxide catalyst that was originally used for methanol synthesis, and the usual one here is zinc chromite. This does not produce an Anderson-Schultz-Flory distribution, but in fact gives you branch products. Usually it's the 2-methyl alcohol that's produced, and therefore if you have a C4 alcohol, you'll get isobutanol, 2-methyl propanol, and this proceeds by a different mechanism, and it's believed to proceed via an aldol condensation, hydrogenation mechanism. This is the base catalyzed aldol condensation. If we have acidity around here, we make hydrocarbons. Okay, when I came into the program, reviewing the literature and some of the other considerations that I've discussed, these are the following points we use as a starting basis for the sorts of catalysts we decided to look at. And we can discuss these a little bit later on, if you like. First of all, we don't want linear alcohol catalysts because we're going to put these into the gasoline pool where we need to have branched materials to raise the octane rating. So we would rather not have the linear alcohols. So therefore we want the isoalcohols. These give you this Anderson-Schultz, the non-Anderson-Schultz-Flory distribution. And if we can get a 1-to-1 mixture of methanol and isobutanol, we can use it to make MTBE. We want high temperature operation, and this is for both kinetic and thermodynamic reasons. The synthesis of the higher alcohols is in a consecutive series of reactions from methanol, gradually building up the chain. And therefore, the higher the temperature, the faster the rate of these consecutive reactions. The thermodynamic aspect of this is that the methanol synthesis reaction is essentially at equilibrium under reaction conditions. And the methanol synthesis is disfavored at higher temperatures. So as we go to higher temperatures, we'll actually be making less of the undesired methanol, and what methanol we are making will be reacting faster to go on to the higher alcohols. So there's both kinetic and thermodynamic reasons for this. Because we want to go to higher temperatures, we are not going to have copper metal present, because copper metal will sinter and deactivate quite rapidly above 300 degrees centigrade. So the formulations I'm going to talk about for the rest of the talk do not contain copper. So what sorts of materials have we been using? Obviously I can't go into the exact compositional details, but I can give you a rough feel for what we're looking at here. They are based on the spinel oxide formulation. It's the 2,3 spinel, where we have both 2 and 3+ metal cations in there. Again, I put the structure of zinc chromide up there to give you a reminder of the sorts of things you can have. Again, this is the high temperature 400-degree operation and the non-Schultz-Flory distribution. We do change the composition of the spinel. We do add alkali and other metals. And one of the metals that we don't add, obviously, here is copper. When we first went through the catalyst optimization program, what I want to do here is just give you a feel for where we stack up with the traditional alcohol synthesis catalyst, which is copper-based, promoted with cesium. This also gives you actually a non-Schultz-Flory distribution. And these are the results from the DOE's pilot plant test down in LaPorte, Texas. So this is a direct comparison, at least in our laboratory microreactors, versus a pilot plant facility. You can notice that the sorts of temperatures they run up to are only as high as 350 degrees because of the presence of copper. Pressure is up to 2,000 psi, 5,000 space velocity. They use a CO-rich syngas feed, which actually favors the higher alcohols, but it cuts down on the overall catalyst activity. The amount of isobutanol that's produced varies anywhere between 9 and 22 weight percent, with a rate of anywhere between 50 to 100 grams per kilogram hour. And this gives you a methanol to isobutanol mole ratio of 8. And the figure of merit, if you like, is for this would be 1. With the best catalyst formulation that we tested in the microreactor system, at 400 degrees, the higher temperatures, 1,000 pounds, using 1-to-1 syngas, we get about 34 weight percent of isobutanol, which works out at a rate of somewhere between 30 to 38 grams per kilogram hour. All these tests were performed at 400 degrees and 1,000 pounds. We had no idea of how these catalysts would perform over a range of different process parameters. So that's what I'm going to go ahead and talk about for the rest of the talk. Just to give you an idea of how non-Schultz-Flory the product distribution is, I always think sometimes the picture is better than 1,000 words. You can see this is clearly not a Schultz-Flory distribution. We make very small amounts of ethanol. The C3 product is basically normal propanol, although we do see isopropanol under reaction conditions. That raises some interesting mechanistic questions that I would rather not go into this afternoon. But it's difficult to see how you can make isopropanol out of the reaction, but we do see it under certain conditions. But the ethanol and normal propanol go on to form the isobutanol. From this, you might assume that the slow step in this reaction is the C1 to form C2 step. So the rate limiting step here is the formation of ethanol from methanol. What I'd like to tell you about is the effect of changing process conversion on the catalyst performance, and we're going to do this in the classical way by both changing space velocity and by changing temperature, and then look at the individual effects of space velocity, temperature, pressure, and syngas ratio on the performance of the catalyst. We're going to find some interesting effects, especially at the lower syngas ratios, in terms of the materials of construction, and we'll talk a little bit about that. And then, having got around the problems here, I'm going to address what happens at 400 degrees centigrade and above, and at higher pressures. Just to give you an idea of what the test apparatus is that we perform these experiments in, it's a stainless steel tubular reactor. We have 1 cc of catalyst. It's diluted with 3 cc's of glass beads. We use a fluidized sand bath to maintain the temperature. In terms of the analytical, we do GC analysis of the product gases. We have 2 columns, one for the inorganics, one for the organics, and we have a cold trap to collect the heavies and the water. And periodically we do GC mass spec analysis if we see anything unusual in the gas chromatograph analysis. These are the typical sorts of reaction conditions that we're going to look at in terms of looking at the effects of the process variables. Unfortunately, these are going to be rather difficult to see because I didn't realize we're going to run into the problem with with the height of the screen here, but I'll try and walk you through here. What we're looking at on the left-hand side is a plot of selectivity of alcohols in percent versus conversion. We want this selectivity to be as large as possible because the inefficiency here is going to be hydrocarbon formation. And as we raise the conversion by changing the space velocity, and here we're lowering the space velocity in order to increase the per pass conversion, you can see the selectivity drops quite dramatically from about 70% all the way down to just above 40%. If we hold that low space velocity and increase the temperature, things get even worse. And by the time we're finished, we're down at a selectivity of about 25%. The problem here is, in fact, that we don't have the optimum alkali level here on the catalyst. So this was a good test for us to make sure that we could go back and correct that. But it gives you an idea of what the sort of problems are. If we're going to operate this process, and we really are going to have to operate it up around 80% selectivity, the only conversion we can get out of the catalyst, at least of this formulation, is somewhere around 15% conversion. And that's not going to be acceptable for an industrial scale operation. The major product, when we're not making methanol, is methane. So at the higher temperatures where hydrocarbon formation is favored, and now I'm talking about the temperature of the catalyst itself, not the external temperature of the gas. As we go into higher conversions and there's a higher heat of reaction, we have a higher intrinsic temperature on the catalyst, we're going to hydrocarbon formation, and the major hydrocarbon product is methane. Not too surprisingly. I'm now going to show a series of plots for the various process parameters. So you may want to get yourselves acquainted with the setup that I have here. First of all, I've got a plot of the alcohol rate versus the space velocity. And you notice that as you go down in space velocity, the alcohol rates fall, but the methanol rate falls at a faster rate than does the isobutanol. So you end up by making more isobutanol relative to methanol at lower space velocities. Again, this is a consequence of the consecutive reaction sequence. The longer the residence time in the reactor, the more chance you have to go on to the subsequent products. And this is reflected, therefore, in a decrease in the methanol to isobutanol ratio, which is our figure of merit, and the lower this number is, the better. So we're going in the direction of goodness, but unfortunately the rates are falling quite dramatically. So here's the effect of temperature. This is actually quite interesting because the effect of temperature on the alcohol rate is actually quite minimal. Temperature is not the big handle here for increasing reaction rate. What's happening is actually the total alcohol rate is falling. And remember I talked about the fact that we're at essentially equilibrium for the methanol synthesis reaction. What's happening is we're going backwards, we're making less methanol, but what methanol we are making is going on to form the isobutanol. Unfortunately, this effect is not very large. But we do see the expected drop in the methanol to isobutanol mole ratio, and here at 420 degrees, we are in fact making a 1-to-1 mole mix of methanol and isobutanol. The big handle for getting the reaction rate up in this system is pressure. And what I'm doing here is I'm plotting again the alcohol rates versus pressure. The range we're talking about here is 700 pounds up to just under 1,400 pounds. And you can see that the rate goes up quite dramatically. We go up by a factor of 3 over the range studied. In this case, though, the total alcohol rate is going up at a faster rate than the isobutanol rate is. So here, we are in fact making methanol at a faster rate than we're making isobutanol. So even though the overall rate is going up, we're making more of the undesired methanol. And again, this is reflected in a rise now in the methanol to isobutanol mole ratio from around 3 at the 700 degrees up to just under 5 when we're around 1300 psi. Well, all these things seem to be relatively easily explained. We come to a problem now when we look at changes in the syngas ratio. Here we're changing the syngas ratio, the ratio of hydrogen to carbon monoxide, from a hydrogen-rich ratio of 2 through an equimolar mixture down to a hydrogen-lean mixture. And what happens here is the rate falls for the alcohol synthesis, the methanol rate falls, the isobutanol rate stays pretty constant. When we go to a 1:2 ratio, spectacular things appear to happen. The rates go up quite dramatically. Here we're making over 200 grams per kilogram hour of isobutanol, and if we could hold this as a snapshot in time, this would be fine. Unfortunately, the reactor plugs, and it plugs on a consistent basis. So we can do this, and we can plug them, and we can run them, and plug them, and continue to do this. Eventually, we tired of that and decided to try and figure out what was going on. You open up the catalyst and look at the actual catalyst bed, and it's covered with a beautiful, clear, waxy deposit. We can take that deposit and have it analyzed, and by golly, it's a wonderful Fischer-Tropsch wax. Starting at about a carbon number of C24 going up to C48, wonderful egg cell distribution peaking at about C28, so it goes up quite dramatically and then tails away. So we're doing Fischer-Tropsch synthesis, but that's not what's plugging the reactor. We can go back to the reactor inlet. And the reactor inlet, this is before we've reached the catalyst, the reactor inlet is plugged with carbon. Okay? And what's going on here is at the low syngas ratios and the high temperatures, we're having CO disproportionation, the Buglard reaction. So we're forming CO2 and carbon. Carbon, first of all, will attack the grain boundaries of the stainless steel reactor wall, which causes flaking of iron and nickel from the reactor tube. That's carried on down onto the catalyst. The catalyst is now a Fischer-Tropsch catalyst with nickel and iron there. And we can come back and look at the ESCA analysis of the catalyst, which I can assure you does not contain copper, it does not contain iron, it does not contain nickel. But the analysis of the catalyst, after running this reaction, it contains iron and nickel. So what's happening is we're having carburization of the tube, eventual plugging, and we're also getting contamination of the catalyst with iron and nickel, which is very disappointing. Okay, so what have we learned from all this? Well, first of all, if we're going to use an iron tube or a stainless steel tube, we don't want to go to low syngas ratios. Not only do we get reactor fouling, but what little gas product we come through is incompletely hydrogenated. So instead of seeing alcohols, we start to see aldehydes, and instead of seeing hydrocarbons, we start to see olefins. Now this might be interesting in another context, but it's not interesting here. So we need to operate at the higher syngas ratio. Operation at the lower space velocities, it's in the direction of goodness in terms of increasing the isobutanol versus the methanol, but we're getting to unacceptably low productivities. We're just not making enough stuff per unit time to make it economical to separate it. If we go to the higher temperatures, we do see the favouring of higher alcohol synthesis over methanol, but now we're going to get into a region where hydrocarbon formation is becoming a problem. So as we go up in temperature, the overall selectivity to alcohol starts to fall. As we go to higher pressures, we do see an increase in the, dramatic increase actually, in the alcohol synthesis, and there's no loss in selectivity here, so we're not in the same regime as we are here. But now methanol is the alcohol that's favoured rather than isobutanol. Well, what can we do from all this? Well, we've sort of fixed where we can run our syngas at. We've sort of decided that we can't go lower in space velocity than this. It looks like we can go to higher temperatures, and possibly we can go to higher pressures. So this is the direction that we went in terms of the catalyst testing. Now remember I told you that we had a problem with the fact that we didn't have enough alkali on the catalyst, so we did go back and re-optimize the alkali concentration on the catalyst. Just to give you a summary of where my thinking is on this. As we go up in temperature, hydrocarbon formation is a problem for us. Okay? Methanol goes down because of the equilibrium constraints, so that's in the direction of goodness. And because it's a consecutive reaction, the isobutanol rate goes up. Notice that this catalyst really wants either to be a hydrocarbon former or it wants to be a methanol former. Okay, so we're trying to go down a very fine line here between Fischer-Tropsch chemistry and methanol synthesis. As we go up in pressure, the hydrocarbon rate, it actually does go down under certain conditions. The methanol rate, however, goes up. The isobutanol rate increases modestly. So if we do a very simple, you might even say simplistic, look at this and just sum the two lines, if we go to higher temperature and higher pressure, we should go to a higher isobutanol rate, and hopefully these two effects will cancel one another out, and we won't have to worry about hydrocarbon formation and methanol synthesis. And it actually works. Okay, here's the same slide that I showed you earlier in the talk, but now we've taken this catalyst here that we corrected the alkali loading for, and we're now running at 440 degrees and 1500 psi. Same space velocity, we are with the 1-to-1 syngas. Now we have a product mix that contains 47% isobutanol. That works out at an isobutanol rate in terms of grams per kilogram hour of 179 grams per kilogram hour. And our overall methanol to isobutanol mole ratio is now down at 2.2. So this is a very clear and distinct improvement over our best and over the conventional art. What do we need to do here? Well, as good as our isobutanol activity is, it's still not good enough. We need to get up by a factor of 2. We still need to get the methanol isobutanol mole ratio down to 1. Process conversion is now about 28%. We'd like to get it higher than that. Catalyst life is still an issue on the scale of the preparation. We're still doing a lot of catalyst characterization, trying to figure out just exactly what the important components of the catalyst are in terms of structure, property, correlations. And we've got to figure out how we're going to run this catalyst. What reactor configuration are we going to run it in? 440 degrees is rather high for a fixed bed process. And the overall process integration of the separations train and how we're going to use this. To close, I'd like to acknowledge again my co-author Dick Nagaki, whose materials synthesis strengths have helped us out here. Paul Rupert, the laboratory technician who ran the catalyst, Jerome Hornbuckle who prepared them, carbide management, Dwayne Dunbeck and Jim Schreck, and also Gary Steigel, Department of Energy. I'd like to thank you for your patience.